show with these calculations is that, in fact, this first inequality in remark 3.2.2, okay, maybe kind of this is the point where we started. We started with this inequality. If we have such an inequality, in fact, this proves, right? This proves theorem 3.2.1. Okay. So, in fact, you will see also in the proof, let me write it here. So, to prove theorem 3.2.1, in fact, it suffices to prove the first inequality in the remark, the first inequality in remark 3.2.2. Does this make sense to you?
Actually, not, but I'm trying to do it. Yeah, I still, but maybe I should to understand this theorem before and remark and trying to do maybe, and
Right.
maybe I can understand, because now I can't say I'm understand. I didn't understand, because I think I need more time to understand this. What does mean this theorem and what does mean this remark? But by the way, I'm trying to do that after we finish this, and today and tomorrow. If I understand something and write something, I will share with you before the first draft, and maybe you can maybe fix it or explain more for me. Write any comment. Yeah, and if I didn't understand still, maybe next week, we can do something. Yeah,
we can talk.
Yeah.
But just to say, if you look at this theorem 3.2.1 just now, you know, what does it say? It says, okay, we have to take dimension to be at least 1, and right. So this theorem.
Yeah, let's dimension
3.2.1
bigger than
Lazard. So some conditions on the dimension, and also some condition on S. So S is less than D over 2. Okay, so I'll explain in a second why this is important. And then what does it say? It says the Sobolev space HS is continuously embedded into LP for P exactly in this range that we said. And so it's HS is continuously embedded into LP for P between 2D, 2 and 2D over D minus 2S. Okay, so there are a couple of elements here to understand. First is, let's forget about this fact that it says HS is continuously embedded. So just if we look at this statement, HS is embedded into LP. This means nothing else than exactly the kind of picture we drew. So HS is a subset of LP. Right? This is all it means. So this picture means exactly HS is embedded into LP. The second thing, now we go back to this continuous. What does it mean it's continuously embedded? So HS continuously embedded into LP. Okay, what does it mean? It means if I take the identity, which goes HS into LP, which says, okay, for I of F is F, for any F in HS. And so this is kind of sometimes called the inclusion map. This is why there this I. This is continuous. So this continuous embedded means this inclusion, okay, let's call it inclusion, okay, is a continuous map. Okay, but let's remember this is also a linear map, right? If to F I associate F, this is linear. So of course I of f equals f, which is the identity or inclusion, is a linear map. Right? We can easily check. I don't know if I take I alpha f plus beta g. This is alpha f plus beta g, and I can view this as alpha I of f plus beta I of g. That is exactly what it means for a function to be linear. Okay, for linear maps, what does it mean continuous? So for linear maps, okay, let's call, I don't know, t between v1 and v2, continuity is equivalent to what we call boundedness, namely when I do t of f in the space v2 that's smaller than a constant time f in the space v1 for any f in v1. Okay, so if I apply this to I of f, if we apply this with let's say I, so t equals I, which goes from hs into LP, so this would be v1, this would be v2. Okay, then we get right, t of f in v2 means I of f in LP bounded by a constant times f in hs, and I of f is f, so this is the same as f in LP. Right, so we get this inequality f in LP bounded by a constant times f in hs. So continuity of this embedding boils down to this inequality that we already talked about, which is from this remark. Right, so we already kind of understand now what it means to have this HS embedded into LP. Sorry, give me a second.
Yeah,
What is it, Akira?